Lesson 5.3, the first derivative test, and we'll also learn how to use calculus to find the increasing and decreasing intervals on functions. So we're going to look at this graph, and we're going to use a red colored pencil and circle all the points corresponding to the local maxima of f. Do not include endpoints. So if I was just looking for maximum points, I would circle these 2 points. I don't see any others on this graph. State the x values where the local maxima of f occur, and those would occur at x equals a and x equals d. At each maximum value, f changes from what to what? So this is my f, and it is changing from increasing. So you can see that your function is increasing here. It stops for a moment, and then starts decreasing. Okay? So it's going to change from increasing to decreasing. Oops. And what about the derivative? If we were looking at the slopes of the tangent lines, we would see like slopes of tangent lines are positive, 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 positive. And then they go to 0, and then they go negative, 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 negative. So they're going from positive to negative. And now we're going to use a blue pencil, and we're going to circle all the points corresponding to the local minima. And do not include endpoints. So it looks like we only have one here. I only see one minima. And state the x values where the local minima occur, just at x equals c. At each minimum value, f changes from what to what? Well, it's decreasing, then it starts increasing. So this would be decreasing to increasing. That's what f is changing from. Now the derivative here, slopes of your tangent lines are negative, negative, negative. They go to 0, and then they're positive, positive, positive. So they go from negative to positive. At a minimum. So this is really important. We're going to be using this a lot. Maximums, the function goes from increasing to decreasing at a maximum, and the derivative goes from positive to negative at a maximum. And at a minimum, it goes from decreasing to increasing, and the derivative goes from negative to positive. So at each local extreme value, f prime of x, the derivative of f is either 0 or undefined. Notice that if I took the derivative, redo that one. If I took the derivative, I would have a derivative of 0 here. See how my slope of my tangent line is 0? I would also have a derivative of 0 here, but the derivative here is undefined. So f prime at d equals undefined. And so you can see that you can have maxes and mins where your derivative is 0 and where it's undefined. And that's something that's really important that you need to be looking at. All right, so now let's go to our next page. It says, using a green colored pencil, sketch a tangent line if possible at the following points and determine their sign. Well, maybe we're going to change mine to black because did it have us do it? Oh no, it's at B. Okay, so we're good. So, but I am going to change it to, I'm going to change it to whatever this color is, some sort of like yellowish orange. I'm just going to put on here yellow, even though it's kind of a gold. at point B, f prime of B is, well, here's my point B. Okay, so my tangent line, it's hard to draw. It's negative, right? It's a negative slope. So my derivative would be negative because, of course, my derivative is the slope of that tangent line. And so describe the change in the behavior of the graph of f at this value. And so notice that, I don't know if you can tell, but look, it's concave down over here. Okay, and then about this point, look, it starts to go to concave up. So when it's asking us to describe the change in behavior of the graph of f at this value, I'm going to say it goes from being concave down to concave up. That is called a point of inflection. When concavity changes, that's a point of inflection. At point D, okay, so I'm looking at D. What is going to happen at D? They want me to, if possible, at the following points, determine or sketch a tangent line. If possible, I can't sketch a tangent line at D. It would be like a teeter-totter. Do you see how you can't sketch a tangent line there? Okay, so the f prime of D is undefined there. Describe the change in the behavior of the graph of f at this value. Well, it's increasing and then it abruptly goes to decreasing. So f is going from increasing to decreasing. At point E, f prime of E is, okay, now this point right here, for a brief moment, it's 0. The slope of that line is 0. Okay, so f prime of E is 0. Describe the change in the behavior of the graph of f at this value. It goes decreasing, decreasing, then it goes to 0 for a brief moment, and then it continues to go decreasing. What else is happening? Well, we've got concave up, and then here we've got concave down. So this is a also a point of inflection going because it goes from concave up to concave down. It wasn't really, it didn't change from, increasing to decreasing or anything like that. It was decreasing and then it kept decreasing. So it was more of the concavity that we wanted to look at, concave up to concave down. Of these 3 points, which 2 are points of inflection? Okay, where concavity changes. Okay, points of inflection are where concavity changes. And so, point B, x equals B, and x equals E. Now, since they did ask for points, you might have wanted to say the point B comma f of B and the point E comma f of E. I did want to mention that because it does say points. So we might have wanted to write it like that. Number 5, if a function f has a relative extrema at a point, then the derivative at the point is either 0 or undefined. Very important that you remember that. Is the converse of the statement also true? So that means if a derivative is 0 or undefined, does it always give me a relative extrema? That would be the converse. Because we just said if a function has a relative extrema at a point, then we know that the derivative is either 0 or undefined. Converse would be, if the derivative is 0 or undefined, do you always have an extrema? And you're going to have to say no, okay? You can see it up here on this graph. You briefly at E had a slope of 0 here, but this was not an extrema, okay? So there's one example. Oops, I went too far. So what point justifies your answer? So we're going to say at x equals E, f prime of x equals 0. But the point E comma f of E is not an extrema of f. Okay, so that is the one that explains that, or that proves that that is true. Proves that the converse is not true. So, definition, increasing and decreasing functions. A function f is increasing on an interval if, for any two numbers x1 and x2 in the interval, where x1 is less than x2, then it implies that f of x1 is less than f of x2. So, basically, if you've got some function, I'm just going to draw some function f. Here's my x1. It has to be less than x2, so you have to have x1 and then x2. Then if your f of x1 is less than your f of x2, and it is here at my f of x1 and then my f of x2, then I have an increasing interval. That's all that means. And if you were talking about a function that is decreasing, you could have, on this function, here's your f of x1, and here's your f of x2, and for that one, your f of x1 is greater than your f of x2. So you can see that that one would be a decreasing function. So now, example number 2. The graph of y equals f of x shown at the right is defined on -3, 7, that closed interval. List the open intervals over which the function is increasing, decreasing, or constant. Okay, so you can see from -3 to -1, you've got an increasing function. So it's increasing -3 to -1. And then it's constant from -1 to 2. And then it starts decreasing from 2 to 7. So it's decreasing on the interval from 2 to 7. It's constant from -1 to 2. Since these look like points, you might want to practice also showing it like that when it's a graph like that. I'm just going to say or. And here's our note. A function is said to be monotonic on an interval if its first derivative, which need not be continuous, does not change signs. And we don't do much with monotonic, but if you were getting a math major, they do talk about monotonic quite a bit. I'm not going to go into that. It's just a little note there. How can we find the values of x on the graph of a function where it is increasing, decreasing, or constant? Some important ideas come to mind. If f of x is a continuous function, then the derivative can only change signs at a critical value. And if f of x is a discontinuous function, then the derivative could change signs at a critical value or at a discontinuity. So think about it. If you've got a discontinuity and that's going to have a derivative that's undefined, you could also have a critical point there. So how to find value or intervals of increase and decrease. So let f be a continuous function on a closed interval a, b. To find the intervals on which f is increasing or decreasing, number one, find the critical values of f, including discontinuities, in the interval a, b. Create a number line chart using these critical numbers and choose x values in between the critical numbers to test the sign of f prime on your sign chart. We call it a sign chart. So note your sign chart is not a valid justification. You must write a clear and concise statement communicating your mathematical language related to sign changes of the derivative, and do not use pronouns. This is mostly for the AP exam, but I am also wanting you to practice like this also. So for example, the function g is increasing on the interval negative 2, 5 since g prime of x is greater than 0. Okay, so let's just do some examples and then this will make more sense because right now I'm thinking that you're thinking it doesn't make sense. So example number 3, find the open intervals on which f of x is increasing and or decreasing and justify. So if we're looking for increasing or decreasing intervals, we are going to find f prime of x. Okay, so here's our f of x. If I take the derivative, I'm bringing the 3 down. It cancels with the 3 in the denominator, leaving me with 2 x to the second. And then derivative negative 2x minus 4. And remember, we're setting it equal to 0. And I'm going to factor a 2 out because I need to factor this. And I think that it's going to be easier to factor if I factor that 2 out. And so we know 2 times 1, we think our 2 is going to be negative, our 1 is going to be positive. This leads us with x equals 2, x equals negative 1. Okay, these are our critical points. So now we're making a sign chart, okay? And it's just like it was on the number line. So if negative 1 is on the left and 2 is on the right, you know, you got to make it like that. The left-hand side will always be the lesser. The right will always be greater. So now you're going to choose a point in between. And, you know, so I'm just going to choose, let's say 0. And we're going to look at what the derivative is at that point. And so I'm looking at putting it into either this or this, right? Or this, right? One of those. These are all the same. It might be easier to put it into this one. So I'm putting in a number in between negative 1 and 2, and I chose 0. And if I put 0 in, I'm going to have positive times negative times positive, which is going to be negative. The next one I'm going to try is a 3. So if I put a 3 in, I get positive times positive times positive, positive. The next one I'm going to choose is a negative 2 because it's to the left of negative 1. I get positive because I'm talking about 2, right? 2 is positive. Then when I put negative 2 in here, I get a negative, so positive times a negative. And then a negative 2 in here gives me a negative, so positive times negative, I get positive. And now, remember, where your derivative is positive, it's in your function f is increasing. Where your derivative of f is negative is where your function f is decreasing. So we're going to say f of x increases on negative infinity, negative 1, union 2 to infinity, because f prime of x is greater than 0. And you could say on those intervals, or yeah, on those intervals. And then you're going to say f of x decreases on the interval negative 1, 2, because f prime of x is less than 0 on that interval. And so, we didn't say, it. That's why it says do not use pronouns. That means don't say, it increases, because they won't know if you're talking about f prime increases or f increases. So you have to make sure you're very explicit when you are justifying why you have these intervals. So when presented with a continuous function, knowing that the sign of the derivative changes at a point, as well as knowing how the sign changes, will give us insight into the existence of the extrema. So that leads us to the first derivative test. And if I was looking for extrema on this problem that we just did here, okay? If someone said, hey, find the increasing and decreasing intervals and then find the extrema. Think about if your function is going from increasing to 0 to decreasing like it is at -1, wouldn't that be a maximum? So I would have known that if I was going from positive to negative, I'm going to have a maximum. If I'm going from negative to positive, I'm going to have a minimum. So look, I'm going from negative to positive here at 2. This is going to be my minimum. So that's basically what the first derivative test is going to tell us, okay? That you can use a sign chart and you can see whether you have a max or a min. If you're going from positive to negative at a critical point, then it's a maximum. If you're going from negative to positive at a critical point, it's a minimum. So now let's read it. Using the first derivative test to determine relative extrema. Let C be a critical number of a function f that is continuous on an open interval. If it's a critical number, that means it's either derivative is 0 or the derivative is undefined. If f is differentiable on the interval, except possibly at c, then f of c can be classified as follows. So now, if f prime changes from negative to positive at c, then f of c is a relative minimum of f. If f prime changes from positive to negative at c, then f of c is a relative maximum of f. If f prime of x does not change signs at c, then f of c is neither a relative minimum nor a relative maximum. So that would look like, if you had a critical point at 2 and your derivative went from positive to positive, you would not have an extrema, okay? Or if it went from negative to negative, you would not have an extrema. So if it doesn't change signs, then you're not going to have a max or a min. So we will explore how to find points of inflection and intervals where a function is concave up or concave down in the next lesson. The following chart will be helpful in summarizing and using correct vocabulary when justifying conditions. So now, you've just got this little function behavior. If your f of x is concave up, if it's concave up, then how would I know that? Well, this would be increasing, this would be positive. The second derivative is positive. That tells you got concave up. Concave down, and you have a decreasing first derivative, you're going to have negative second derivative. Okay? So if your function is increasing, your first derivative is positive. If your function is decreasing, your first derivative is negative. Okay? And that's just, I don't know, just kind of trying to put all this stuff together. So let's look at example number 4. Given the function f of x, find the open intervals on which f of x is increasing or decreasing and justify. So everyone should remember that to do that problem, we are going to find the derivative. So we've got 4x to the third minus 16x. We are going to set it equal to 0. And factor out what is common. I know a 4 and an x is common. X squared minus 4 is left. That gives me x equals 0, x equals 2, and x equals negative 2. Sorry, I did not factor it, but you know how I got that. And so now we would make our sign chart, and negative 2 is our smallest, then we have 0, then we have 2. We're going to be looking at f prime, and we're going to choose values in between. So if I chose 1 to put into my, I'm probably going to put it into this form of my derivative. So if I put 1 in, I'm going to have a positive times a negative times a positive. So that's going to end up giving me a negative. If I put a 3 in, I would have a positive times a positive times a positive, which would give me positive. If I put a negative 1 in, I would have a negative times a negative times a positive, which would give me positive. And if I put a negative 3 in, I would have a negative times a negative times a negative, which is negative. So hopefully you can see that. I'm sorry I squished that all together in there, but you can see that, and since these are critical points, that means that from negative infinity to negative 2, your derivative's negative. From negative 2 to 0, your derivative's positive. From 0 to 2, your derivative's negative. And from 2 to infinity, your derivative is positive. So increasing and decreasing for this particular problem, we would say f of x is increasing on negative 2, 0, union 2 to infinity, because f prime of x is greater than 0 on those intervals. And then we would also say f of x is decreasing on negative infinity to negative 2, union 0 to 2, because f prime of x is less than 0 on those intervals. Now, part B, that was your part A. And, you know, basically part 1 found our critical points. Part 2 was finding our sign chart, or creating our sign chart. And part 3 was justifying how we know that these are our increasing and decreasing intervals. Okay, so that was all part A. And part B, determine the x values of any local extrema of f of x and justify. So if you remember, we were saying that if a derivative goes from negative to positive, then at that critical point, you have a minimum. If it goes from positive to negative, then at that critical point, you have a maximum. And if it goes from negative to positive, at that critical point, you have a minimum. So that's using the first derivative test, and now we're just going to explain it. So a minimum occurs at x equals negative 2 and x equals 2. Because f prime of x changes from negative to positive at those x values. A maximum occurs at x equals 0. Since f prime of x changes from positive to negative at x equals 0. Okay? And basically, that is using your first derivative test, because that's what your first derivative test says. Hey, if you've got a critical point and your derivative changes from negative to positive at that critical point, it's a minimum. If you got a critical point and your derivative changes from positive to negative at the critical point, then it's a maximum. All right, so let's go to example number 5. For each statement below, sketch a function that represents the results of the first derivative test for a continuous function, y equals f of x, with a critical number at x equals c. F of x has an absolute minimum at x equals c because f prime of x changes sign from negative to positive at x equals c. Okay, so they just want us to draw a picture of something that would look like that. And, you know, yours could just be as simple as, just like a upward facing parabola. I went ahead and kind of gave it a little bit of another twist and turn there. But you can see that my f prime of c is 0, and it goes from negative slopes of tangent lines to positive slopes of tangent lines on either side. And then for part B, f of x has a local maximum at x equals c because f prime of x changes signs from positive to negative at x equals c. And so for this one, I kind of went like this, and I went like that, just to show it. And there's my maximum, and it goes from positive slopes of tangent lines to negative, so my derivative goes from positive to negative at x equals c. And that was my example. So my f prime of c equals 0, and it was going from positive to negative. Part C, f of x has no local extrema at x equals c because f prime of x is greater than 0 for all x greater than 0 and is strictly monotonic. Okay, so this would mean an always increasing function. Okay, always increasing, but has a derivative at c. Okay, has a derivative of 0 at c, just like we did on that other one that was when at the very beginning of the notes, it flattens out, but the derivative is positive, 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 but then it goes to 0, but then positive, positive, positive. Do you see how those derivatives don't change there? So that's what this would look like, and it's strictly monotonic. So since f prime of x is negative immediately on either side of x equals c, the function f of x has neither a local maximum nor a local minimum at x equals c. So for this one, it would be the same thing, only going the other way. Okay, because we would have negative slopes of tangent lines. It would briefly go to 0, ever so briefly, and then negative, negative, negative slopes of tangent lines again. Okay, so that's what would be a good example of that. All right, so now, example number 6. Oh, shoot.